So the recording is on. So ang topic natin for today is about ultimate stress design in beams. So part 1 to of the many parts ng gagawin natin. Probably 2 to 3 parts now. Okay, so for the topic outline for today, meron tayong ultimate stress design method, derivation and all. The same time, yung mga design assumptions natin and isang sample problem. If aabot tayo doon sa time. Kasi yesterday, hindi inabot yung time namin primarily because of the derivation process na medyo mahaba. Okay, so the ultimate stress design, it was conceptualized sa early 1940s. The same time sa kino-consider nito yung ultimate strength of both concrete and steel in the design. So at the same time, the concept was created in 1956 as an appendix in the ACI code, which introduced certain load factors derived from the factor of safety. So bukod doon sa factored loading na ginagawa natin sa pagde-design, nag-introduce din sila ng factor of safety para mabigyan ng allowance na ma-bear ng load yung structure natin. So it is widely used because of its capability na maglabas ng design na economical, at the same time yung pagiging rational. Like interdependent yung concrete and steel, which makes USD an efficient way to design a structure. Okay. So ano ba yung iniba ng ultimate stress design doon sa working stress design na ginagawa noon? So sa working stress design, yung ginagawa nung mga panahong hindi pa uso yung ultimate stress design, ang ginagawa is primarily gumagamit ng linear theory. Wherein sa linear theory, let's say meron tayong concrete beam, tapos bounded by the neutral axis. Kadalasan, ang nangyayari is yung compressive area natin ay merong equivalent ng steel. Bagay yung steel natin, yung capability ng steel to withstand forces ay nakadepende dito sa capability ng concrete. Baga parang may, for every strength ng concrete, merong equivalent ng steel. Yun yung ratio na ginagawa sa linear theory. Whereas sa ultimate stress design, ang kinoconsider natin is yung ultimate strength ng steel and concrete ay independent. So therefore, yung internal capabilities nila is na-utilize as well. Ngayon, although parehas din naman ng interaction in terms of compression and tension dito sa working stress design and ultimate stress design, ang iniba lang sa una is hindi equivalent strength ang ginagamit natin sa steel as compared kay concrete. Baga, same time na compressive strength ang ginagamit natin sa concrete pero pagdating sa steel, magkaiba na. Sa ultimate stress design, ang kino-consider natin is yield strength. So, yung ability ng material natin na steel to yield or to deform permanently, ang limit natin sa ultimate stress design, whereas sa working stress design is yung tensile strength, which makes the steel fail. So, ibig sabihin, sa working stress design, kino-consider pa natin na hindi pa failure yung pumapaling na yung bakal. Whereas sa ultimate stress design, pumaling lang yung bakal natin, considered as fail na. Ngayon, sa ultimate stress design, iniba rin is, bukod doon sa factored loading, na parehas sila ng working stress design, gumagamit din tayo ng factor of safety para doon sa ultimate stress design, which is considered as the strength reduction factor. Whereas sa working stress design, although meron tayong factored loading, wala tayong factor of safety. Ibig sabihin, yung strength reduction factor, walang kino-consider sa working stress design or kino-consider natin na 100% yung ma-absorb ng concrete beam natin. Ngayon, another thing sa ultimate stress design is because of yield strength ang kino-consider natin doon sa ultimate stress design, nagpe-permit tayo ng more flexible and economic design. Meaning to say, kung economic design, pwede nating sabihin na lesser yung reinforcement. Lesser reinforcement pero larger, pwede sabihin natin na larger yung member. Pero, kino-consider natin na magkakaroon siya ng lesser reinforcement. Or, pwede natin gawin na small member with more reinforcement. So, may choices ka sa ultimate stress design. Whereas sa working stress design, hindi na natin magagawa yon because yung percentage ng steel is percentage din ng concrete. So, medyo skeptical tayo in terms of working stress. Ngayon, under ultimate stress design, lastly, so sa pagkakasabi kanina na designed for elastic and plastic behavior, dito ngayon pupunta yung yield point and yung tensile strength. Alam natin na kapag nag-yield yung material natin, hanggang doon lang siya sa point na magbe-bend siya or magkakaroon na ng permanent failure. Pero kapag tensile force ang pino-consider natin dito sa plastic behavior, meaning to say, umaabot na tayo doon sa point na magfe-fail na siya because ang limit natin is nasa permanent deformation. Question so far, or malinaw ba? Or naririnig ba ako?
Yes po, sir.
Okay. So, questions dito sa concept ng ultimate stress design. Wala pa?
Wala pa po.
Okay, wala pa. Ngayon, punta tayo sa assumptions. So sa assumptions, meron tayong 4 na assumptions na dapat sundin sa ultimate stress design. So first assumption natin is yung load increase depending on the factored load combinations. So meaning to say, kailangan nating sundin yung section 405 ng structural code. Next. So yung strength reduction factor is considered as the factor of safety. Kumbaga, ino-optimize natin yung strength ng structure natin para may allowance tayo na pwedeng ibigay doon sa structural member in case of failure or in case of attaining the ultimate capacity. Ngayon, another assumption is yung concrete sections natin can actually reach their flexural capabilities or capacities if meron tayong net tensile strain na equal to 0.003. Saan natin makikita ngayon yan? Kung net tensile strain ang pinag-uusapan natin, suppose meron tayong ulit concrete beam with a specific reinforcement bounded by the neutral axis. Ngayon, kapag nagko-consider tayo ng strain, yung strain can also be denoted doon sa flexural stress diagram natin. Ngayon, yung strain ng concrete and yung strain ng steel are different because number one, different yung material composition nila. At the same time, iba yung orientation ng forces na kinikater nila. Yung steel natin, alam natin na yung steel ay para doon sa tension, whereas yung concrete ay para dito sa compression. Ngayon, sinasabi na yung strain daw ay equal to 0.003. Pero yung sa steel natin, may dalawang dapat tayong i-assume. So mamaya, ipapakita ko kung ano ba yung dapat nating i-assume doon. Pero sa steel, ang strain ng steel is equal to either yung yield strength or yung tensile strength all over the modulus of elasticity of steel. Anyone who can tell kung ano yung modulus of elasticity ng steel base doon sa construction materials ni last semester? Ano yung modulus of elasticity ng steel? Modulus of elasticity of steel is equal to
200,000 megapascals.
200,000 megapascals. Okay. So yung 200,000 megapascals na yan ay gagamitin natin in order for us to find the net tensile strain of steel. Ngayon, depende sa case kung transition or tension control, then nagdi-discuss natin later on. Okay. So at the same time then, pwede nating i-assume na yung compressive stress distribution of concrete can be represented by the corresponding stress-strain relationship between concrete and reinforcement. So yung stress distribution can be denoted as a function of the strain considering na iba rin yung mga forces na dapat nating gamitin. Okay. So, proceed tayo sa, before pala tayo mag-proceed dito sa questions with regards to assumptions. Wala?
Wala po, sir.
Wala pa. Okay. So, proceed tayo sa pagdederive. Ngayon, magpapalit ako ng screen. Baka kasi mangyari yung nangyari yesterday na nagkaroon kami ng technical difficulties. So, yan. Lipat tayo ng mode. Okay. So, for our assumption, meron tayong concrete beam na loaded. At the same time, meron tayong area in compression and area in tension na designated. Yung area in compression and area in tension is bounded by the neutral axis or separated by the neutral axis, which denotes that neither compression or tension is experienced in the neutral axis. Meaning to say, sa neutral axis natin, ang stress natin ay equal to 0. Ngayon, since wala tayong stress na na-experience doon sa area in sa neutral axis, meaning to say, as we progress, either doon sa upper side or lower side, meaning to say, nagkakaroon tayo ng either compression or tension. Depende sa orientation ng flexure. Okay. Suppose meron tayong area in compression and area in tension. Sa ultimate stress design, kino-consider natin na yung area in tension ngayon, yun nagko-compensate doon sa tension na nararamdaman ng concrete. Yung area in tension would denote the reinforcement. Ngayon, yung area in compression na concrete, sa under ultimate stress design, hindi raw siya linear in nature. So meaning to say, meron siyang curve na form while distributing yung compressive stress dito sa area in compression, which resulted to a compressive force in relation to the area. Given na, syempre, by means of approximation or by means of further studies, nagkaroon ngayon ng innovation in terms of the ultimate strength design na na-approximate ngayon in linear terms yung compressive block natin. Ang compressive block daw natin ay bounded by an approximate value of the compressive block A, which is a fractional part of the total area in compression, which is denoted as small letter C. Ngayon, itong small letter C natin is yung actual na depth natin for compression. Pero dahil curve yung area natin, ngayon nagkaroon ng innovation na na-approximate nila into a fictitious depth denoted as A. Wherein, itong compressive block natin is actually experiencing 85% of the 85% of the total compressive strength. So meron tayong 0.85 na F prime C. And then all throughout the beam, meron tayong base na constant. Base which is equal to B. Ngayon, itong stress block daw natin is acting doon sa mismong compressive area natin bounded by the fictitious depth A. Wherein doon daw sa centroid ng compressive block ngayon, nag-o-occur yung compressive force na C. Try natin palitan ng kulay para medyo ma-visualize natin. So, itong compressive force daw na equal to capital letter C can be distributed dito sa area in compression. Ngayon, doon sa area in compression, base dito sa figure natin ng stress diagram, ano yung magiging compressive force ko? Meron tayong depth na A, meron tayong width na B, and meron tayong length na 0.85, F prime C. Compressive force natin ngayon, base dito sa figure, is now equal to ilan? Kumbaga, ang clue niyan, ang context clue is tumatama doon sa concrete beam natin yan throughout its area in compression. Ano ngayon yung magiging compressive force natin? Base dito lang sa figure na to. Baga kinukuha natin yung volume ng stress block natin. Wherein yung stress daw natin ay directed dito sa compressive area natin. Kinukuha natin yung volume nitong compressive block na to, therefore yung compressive force natin is equal to ilan? Meron tayong sides na 0.85 F prime C, meron din tayong side na A, and meron tayong side na B. Compressive force is now equal to 0.85 F prime C A B. So itong compressive block na to, ngayon yung magiging resulting compressive force natin na na-generate all throughout a specific area of compression. Ngayon, kaya daw yung A ay hindi tatama dito sa neutral axis, kung mapapansin ninyo, because yung A natin yung value ng A is a fractional part of C. Wherein sa fractional part ng C, may minumultiply tayo na beta 1. Wherein yung beta 1 daw, according sa structural code, ay merong condition. Kapag yung F prime C natin is less than or equal to 28 megapascals, ang beta 1 natin is equal to 0.85. Pero, kung halimbawa man na yung beta 1 natin ay, or yung F prime C natin rather, ay maging greater than 28 megapascals, pero less than 55 megapascals yung F prime C natin, gagamit tayo ngayon ng equation. Iusog ko ng onte. Wait lang. Okay. So balik tayo. Kung yung F prime C daw natin is less than 55 megapascals, but yung F prime C natin is greater than 28, yung beta 1 natin ay may equation tayong gagawin. So this is 0.85 minus the quantity of 0.05 multiplied by F prime C minus 28. Ano na pala, hindi nakakasya. F prime C minus 28 divided by 7. Yan ngayon yung equation na gagamitin natin for beta 1 if in case na yung F prime C natin is greater than 28 but less than 55. Pero kung yung F prime C natin is greater than 55, ang beta 1 natin is equal to 0.65. When in case, yung beta 1 natin should never be less than 0.65. So ang least value ng beta 1 natin is 0.65 and yung greatest value natin for beta 1 is 0.85. So in between 0.85 to 0.65 lang yung beta 1 natin. Okay. So other than that, the compressive force, yung B natin is yung base ng beam. Yung F prime C natin is yung compressive strength. So yan, that's all there is para sa compressive force. Ngayon, syempre kung merong compression, dapat din merong tension na magko-compensate doon sa compression natin, which is denoted as the tensile force T. Yung tensile force natin is dependent doon sa area ng steel. Wherein, yung area ng steel would depend doon sa bilang ng bakal na ini-install mo and at the same time doon sa diameter. Ngayon, within this specific area, meron tayong kinoconsider na yield strength. Yung yield strength ulit natin is equal to Fy. Within this yield strength or tinatawag nating Fy, alam natin na yung yield strength all throughout the reinforcement ay pare-parehas na. Therefore, paano natin mako-consider or makukuha yung value ng tensile force? Yung value ng tensile force natin this time would be equal to the area of steel reinforcement multiplied by the yield strength. Ngayon, since kung mapapansin nyo dito sa concrete beam natin, meron tayong reinforcement na located hindi doon sa mismong bottom fiber ng nung concrete beam natin. At kung mapapansin ninyo rin, tinapat natin yung bottom area doon sa centroid ngayon ng steel. What does this denote? Dinedenote nito na ang tension ay na-experience lang dito sa area in tension. So, yung area in tension lang natin ay yung steel reinforcement. So, wala tayong tension sa concrete mismo. Given na yan na mismo yung area in tension, meaning to say, hindi naman yung nominal depth ang kino-consider natin sa design. Ang kino-consider natin sa design is yung effective depth. Sa effective depth natin is mula dito sa top fiber in compression hanggang doon sa centroid ng steel. So meaning to say, hanggang doon sa center of gravity ng steel, yung effective depth. Ngayon, considering na meron tayong compressive and tensile forces, ano yung mapapansin natin? Yung force in compression saka yung force in tension ay dalawang forces na nag-a-act at different direction. So ano yung po pwede nating maging hint doon? Anong klaseng forces sila? Anyone who can answer? Kung meron tayong dalawang forces acting at different directions, ano yung posible nilang na-generate? Balik tayo sa engineering mechanics nyo. Kung meron tayong dalawang different forces acting at kung meron tayong dalawang forces acting at different directions, ano yung na-generate nila?
Resultant force, sir.
Resultant? Hindi. Equilibrium?
Couple, sir.
Yon. Couple, di ba? Couple forces sila na ang na-generate nila ay moment, di ba? Ngayon, kung couple forces sila, ano yung pwede nating sabihin? Or ano yung pwede nating i-assume between compression and tension? So, compression and tension are couple forces. Therefore, ano yung pwede nating sabihin? Kung couple forces sila, ano yung distinct between couple forces bukod sa nag-generate sila ng moment at a specific distance?
Same po sila ng load.
Same sila ng load or same sila ng magnitude. Meaning to say, yung compression natin is equal to tension. Which means that 0.85 F prime C AB is equal to AS Fy. Okay? So kung same yung compressive and tensile force ng magnitude, paano natin ngayon makukuha yung moment between them? Ano yung pwede nating gawin? So, meron na tayong first equation. Meron na tayong A is equal to beta 1C. Let's say this is second equation. Ngayon, proceed tayo doon sa baba. Yan. So nakikita naman yung 0.85 F prime CAB is equal to AS of Y. Recap ulit na pumunta tayo doon sa effective depth, wherein yung effective depth daw natin ay mula dito sa taas ng compressive fiber natin or dito sa dulo ng compression hanggang doon sa centroid ng tension. Yan daw yung kino-consider natin as effective depth. Ngayon, considering na yung neutral axis ay hindi aabot yung compression doon sa neutral axis, at the same time, meron tayong fictitious depth na equal to A. Alis natin dito para medyo malinaw. Yan. So, yung fictitious depth daw natin in compression is equal to A. Ngayon, may compressive force ulit tayo na nag-a-act doon sa centroid ng compressive block natin na equal to 0.85 F prime C A B. Whereas meron tayong tensile force na nag-a-act doon sa centroid ng reinforcement na equal to AS FY. Ngayon, in order for us to generate a moment, kailangan natin ng distance, di ba? Let's say this is now coined as the nominal moment. Okay. Yung nominal moment ma-generate kung merong specific distance between compression and tension. Ngayon, given yung different depths natin, between compression and tension, meron tayong ma-generate na distance. Alam natin daw na yung compression force or yung compressive force natin ay nag-a-act doon sa center of gravity ng compressive block natin with the depth A, and yung tensile force natin ay galing doon sa compressive block sa itaas, sa top fiber natin, hanggang doon sa centroid ng reinforcement. Ano ngayon yung distance na to? Let's denote it as Z. Yung nominal moment natin can now be equal to either compression or tension multiplied by Z, wherein Z is equal to ano na ngayon?
D minus 1/2 A po.
D minus 1/2 A. So this is D minus A over 2. Ngayon, ano yung mapupulot natin dyan? Kung meron na tayong nominal moment, paano natin makukuha ngayon yung ultimate moment? Yung ultimate moment natin, so base sa ultimate stress design, ng ultimate moment natin yung magdidictate sa kung ano ba dapat yung magiging internal capacity and yung external force na pwede natin i-apply or yung allowable doon sa structure natin. Yung ultimate natin na moment, therefore, is equal to the strength reduction factor multiplied by the nominal moment. Ngayon, ano ba yung significance ng ultimate moment sa nominal moment? So, yung ultimate moment natin is yung applied force natin. Whereas, yung nominal moment natin with the strength reduction factor is considered as the allowable. Ngayon, within this bounded assumption, makikita natin na yung ultimate moment na MU or yung applied natin na force is galing doon sa external forces or galing doon sa load na dinadala ng structure natin. Whereas yung strength reduction factor multiplied by the nominal moment is yung allowable force na po pwede nating i-incorporate dito sa concrete beam natin. Ayun. Given na yung nominal moment natin is equal to either compression or tension multiplied by the moment arm. Alam natin na yung compression ulit is 0.85 F prime CAB. And then yung tension is equal to ASFY. We take note of the following ratios. Meron tayong kino-consider na reinforcement ratio. Wherein yung reinforcement ratio natin, denoted as rho, is equal to the area of steel reinforcement all over the base of the beam multiplied by the effective depth. Okay, so rho is equal to AS over BD, which denotes that the area of steel reinforcement, therefore, is equal to the reinforcement ratio multiplied by the base and the depth, effective depth of the beam. Ngayon, kung meron tayong reinforcement ratio na ganito, baka po pwede nating alamin kung paano ba kukuhanin ngayon yung nominal moment. Given tong case na to, na AS is equal to rho BD. At the same time, alam natin ulit from equation 2, let's say this is equation 3 now. Ang equation 2 natin kanina, alam natin na A is equal to beta 1 multiplied by C. So, iwan natin dyan yan. Ngayon, yung pagko-compute natin dito, alam natin na yung nominal moment is equal to the compressive or tensile stress or tensile force multiplied by Z. Saan ngayon po pwede natin incorporate yung value ng AS? Dito sa tensile force. So yung nominal moment natin, we can say that this is equal to AS multiplied by Fy multiplied by D minus A over 2. From this, pwede nating sabihin na yung ultimate moment is equal to the strength reduction factor multiplied by AS Fy multiplied by D minus A over 2. Ngayon, kung meron tayong equation ng ultimate moment, let's say this is equation 4. We can actually incorporate yung values ng 2 and 3 doon sa 4 natin. Diba? Pero, considering na yung equation 2 is iabang natin to. So, try nating antayin kung saan siya po pwedeng gamitin. Alam natin sa equation 1 earlier na meron tayong 0.85 F prime C AB is equal to AS Fy. We can actually tell that the value of A in equation 1 is equal to, ano na ngayon? Kung ita-transfer na, ita-transpose natin or i-factor out natin yung any other term dito sa left side natin, ang value ng A should be equal to AS Fy all over 0.85 F prime C B. Ngayon, itong beta 1C, kahit hindi muna natin gamitin. So, i-omit muna natin yung fact na yung equation 2 ay magagamit natin. Let's say yung A na to is equation 4. Tapos, ay hindi, sorry. Equation 5 na. Okay. If we incorporate equation 3 and equation 5 at equation 4, pwede natin sabihin na yung ultimate moment natin can be equal to the stress reduction factor multiplied by AS or rho BD multiplied by Fy multiplied by the quantity of D minus yung A natin na equal to ASFY, pero alam natin na ang AS is equal to rho BD. So another term multiplied by Fy all over 2 times 0.85 F prime C B. Wait lang, kukunin ko lang yung charger ko saglit. So, yung rho BDFY natin is incorporated na doon sa dalawang spaces natin na may common terms. Ngayon, ano yung mga pupwede nating i-cancel? So dito, maghahanapan na tayo ngayon ng pupwedeng i-simplify. So sa mga bagay na pupwede nating i-simplify, dito, pwede nating i-simplify this time yung itong base, di ba? Pwede nating alisin yan. At the same time, meron ba tayong pupwedeng i-factor out dito sa term na to? Meron tayong D minus the quantity of rho dFy all over 2 times 0.85 F prime C. Meron ba tayong pwedeng ilabas na term dito?
Yung D po.
Yung
D.
value ng D. Okay. So, pwede natin sabihin na meron tayong phi. So, yung phi, yung strength reduction factor multiplied by rho na reinforcement ratio times BD Fy multiplied by D times the quantity 1 minus rho Fy all over 1.7, so 2 times 0.85 F prime C. Ngayon, pwede na nating sabihin na ang final equation natin for ultimate moment is equal to rho ay phi multiplied by rho BD squared Fy multiplied by 1 minus rho Fy all over 1.7 F prime C. So yan ngayon yung ultimate moment natin. Whereas, paano natin kukunin yung nominal moment kung meron tayong ultimate moment na ganito? Pwede lang natin sabihin na yung nominal moment natin is walang stress reduction factor. Kasi alam natin na ang ultimate moment ay may stress reduction factor. So therefore, yung nominal moment capacity natin is equal to rho BD squared Fy multiplied by 1 minus rho Fy all over 1.7 F prime C. Yan ngayon yung nominal moment natin. So therefore, yung ultimate moment natin is this one. Bukod dyan sa reinforcement ratio, meron ulit tayong kino-consider na design ratio. So yung design ratio natin na R is just equal to the ultimate moment all over BD squared. Therefore, yung ultimate moment natin is equal to RBD squared. Ngayon, bukod sa mu all over BD squared, yung value ng R, kung titingnan natin itong equation na to, paano natin madederive dito yung value ng R? Ulitin natin. Ang design ratio daw na R is equal to the ultimate moment all over BD squared. Therefore, yung R natin, base dito sa equation ng mu, is equal to, ano ngayon? Cancel out lang itong BD squared. Meron tayong phi times rho times Fy multiplied by 1 minus rho Fy all over 1.7 F prime C. Yan ngayon yung value ng design ratio natin. Nakaka-catch up so far?
Sir, yung sa huli lang po yung sa R. Pwede pong
Okay.
paulit.
Sige. So, yung sa R natin, which is considered as the design ratio, meron tayong base equation for the design ratio na it is the ultimate moment divided by BD squared. Therefore, pwede nating sabihin na yung ultimate moment can be equal to the design ratio multiplied by BD squared. In this principle, pwede natin ngayong tingnan itong equation ng mu na na-derive natin earlier na baka po pwede nating tingnan kung paano natin hahanapin yung value ng R. Since mu is equal to phi rho BD squared multiplied by Fy times the quantity na 1 minus rho Fy all over 1.7 F prime C. Dito sa ultimate strength, meron tayong BD squared na term. So meaning to say, if R is equal to mu all over BD squared, ang value ng R ngayon is, aalisin lang natin yung BD squared sa term ng mu, which is equal to phi rho Fy multiplied by 1 minus rho Fy all over 1.7 F prime C. Questions pa?
Okay na po, sir. Thank you po.
Okay, thank you. Questions so far? Ngayon, since at some point, alam na natin kung paano makukuha yung nominal moment followed by the ultimate moment and the design ratio, without forgetting yung reinforcement ratio natin and yung value ng A. So, nagre-recap lang tayo. Same time, yung mga couple forces natin, gagamitin natin siya ngayon sa iba pang derivations. Ngayon, over strength reduction factor, yung strength reduction factor natin na ang value ay phi, paano natin ngayon siya kinukuha? So according sa structural code, ang strength reduction factor ay nakadepende dito sa values ng tensile strength and yield strength of steel. Ngayon, dito sa dalawang to, magre-revolve yung values ngayon ng strength reduction factor na merong maximum value na 0.9 and lowest value of 0.65. Ngayon, sa case natin, ang tinitingnan natin dito is yung relationship between yield strength, tensile strength, and the strength reduction factors. Kung mapapansin nyo, kung compression controlled ang ino-consider natin sa pagde-design natin, ang yield strength natin is less than Fy, ang magiging value ng strength reduction factor natin is equal to 0.65 for other cases. Ngayon, kung spiral ang kino-consider natin na structural member, yung bilog ang cross-section, meaning to say, ang magiging compression control niya is equal to 0.75. Pero in other cases na rectangular yung beam natin or triangular, ang kino-consider natin ngayon is equal to 0.65. Now, sa cases na meron tayong tension-controlled na structure, ang strength reduction factor natin is equal to 0.9. Pero what comes in between? Yung transition na tinatawag natin is meron tayong range ng values from 0.65 hanggang 0.9. Or kumbaga parang it should be less than 0.9 but it must be greater than 0.65. Ngayon, kung i-derive natin yan, paano natin gagawin? Okay. So, yung conditions natin between Fy and Fs are as follows. So, if yung Fy natin is greater than Fs, pwede nating i-consider yan na compression control. Tapos, kung yung Fy natin or yung meron tayong 1,000 na limit papunta doon sa tension and meron tayong Fy na papuntang compression. So if yung 1,000 natin ay greater doon sa Fy, sa Fs rather, pero yung Fs natin ay greater kay Fy, dito pa lang natin sasabihin na this is in transition. So mapapansin nyo dito, sa relationship ng graph natin, yung 1,000 is, alam natin na greater siya doon sa Fs natin, since yung Fs natin ay nandito pa sa kabilang side, so kino-consider natin yung Fs ay nandito sa gitna. Pero yung Fs natin is greater doon sa Fy, therefore nagkakaroon ngayon ng transition. Pero kung yung Fs natin ay greater sa 1,000, so yung 1,000 natin papunta doon sa right, doon na niya ma-meet yung Fs, pwede nating sabihin that this is tension control. Ngayon, under the circumstances, yung transition lang ang walang specific value for strength reduction factor. So ano yung dapat nating gawin? Meron tayong upper limit na 0.9 and 1,000. Meron tayong lower limit na 0.65 saka Fy. So assuming na other cases Ngayon, ano yung pwede nating gawin para makuha yung strength reduction factor in transition? Paano natin siya masasolve? Kung meron tayong upper limit na 0.90, tapos meron tayong 1,000 in terms of megapascals yan. And then sa lower limit natin, meron tayong 0.65 And then, ang kinoconsider natin ay Fy. Ano ngayon yung gagawin natin? Ano yung pwede natin gawin? Since meron tayong Fs dito, and meron tayong strength reduction factor. Anyone who can guess kung ano yung pwede natin gawin para makuha yung value ng phi or ng strength reduction factor? Yan. Yung pagkakapwesto ko na yan, context clue na yan kung ano yung gagawin natin. Ang kailangan natin gawin ay linear interpolation. Okay. So, through linear interpolation, ano na yung pwede nating gawin? Through linear interpolation, pwede nating sabihin na yung 0.9 so meron tayong 0.9 minus yung lower limit natin na 0.65 all over yung 1,000 natin na upper limit minus Fy is equal to yung mga unknowns na ngayon. Yung unknown natin na strength reduction factor minus yung lower limit natin na 0.65 all over yung unknown ulit or yung known value natin like so, yung Fs since may range yan, minus Fy. Dito sa case natin, pwede nating sabihin ngayon na yung 0.9 minus 0.65 ay 0.25. So pwede ko sabihin na 0.25 multiplied by Fs minus Fy is equal to phi minus 0.65 multiplied by 1,000 minus F1. So in this case, meron tayong 0.25 multiplied by Fs minus Fy all over 1,000 minus Fy is equal to phi minus 0.65. Therefore, ano ngayon yung value ng strength reduction factor? Yung strength reduction factor natin this time is equal to 0.65 plus. Okay? So plus 0.25 multiplied by Fs minus Fy all over 1,000 minus Fy. So yan ngayon yung strength reduction factor in transition for other cases. Ngayon, paano natin gagawin yung sa spiral? Yung sa spiral, ang gagawin lang natin is 0.75 ngayon yung lower limit natin instead the 0.65. Kung spiral yan, ang strength reduction factor natin this time is equal to 0.75 plus 0.15 multiplied by Fs minus Fy all over 1,000 minus Fy. Ito ngayon ay para sa spirals. Okay. Saan ulit natin ginagamit yung strength reduction factor? Sa pagkuha ng or saan importante is itong strength reduction factor natin?
Sa may ultimate moment po, tsaka
Okay.
sa R.
So sa ultimate moment natin, ginagamit yung strength reduction factor and doon sa design ratio. So importante na kung halimbawa hindi nyo makabisa itong equation na to, pwede nyo namang i-derive. So in this case, binabox ko lahat ng mga pwedeng kabisahin para kung sakaling hindi kayo sipagin mag-derive, kabisa na lang. Pero might as well aralin pa rin kung paano dinederive lahat itong formulas. Okay? Tanong.
Sir,
Yes.
bakit po sa module po, minus po yung saan?
Ayun. Maki-correct, please. Or hindi. Sige, magsisend ako ng revision ng magsisend ako ng revision nung module natin. Oo nga, minus pala yun nandito. Sige. Teka lang. Isasend ko na sa GC ng mga mayor. Revise module for strength reduction factor. In transition. Plus instead of minus. Okay. Questions pa? Thank you for noting na mali yung nailagay ko doon sa module. Okay. Take note ulit na yung strength reduction factor sa transition should be greater than 65. That should be greater than 0.65. But it should be less than 0.9. So ibig sabihin, kapag naging mas mababa sa or maging equal siya sa 0.65, may mali kayo. Or kung mas malaki or equal sa 0.9, may mali kayong ginawa dito sa strength reduction factor. So dapat ito lang yung magiging range ng value. Questions pa before tayo mag-proceed? Wala pa?
Wala na po, sir.
Okay. So, i-ano natin. So, paano ngayon tayo magde-design ng reinforcement na kailangang mag-yield? Alam natin kanina na meron tayong kinuha na reinforcement ratio na equal to AS all over BD. Paalala natin na yan ay reinforcement ratio. Pero kung titingnan natin, meron tayo dapat na limit para masabi natin na yung design natin ay yielding. Suppose na itong reinforcement ratio na to is yung actual reinforcement ratio. Actual siya kasi tinitingnan natin yung ratio ng actual reinforcement area doon sa dimensions natin. Para malaman natin na nag-yield yung design, may kailangan tayong sundin. Ang kailangan nating sundin is yung ratio between the actual reinforcements na kailangan yung actual reinforcement daw natin ay less or equal doon sa maximum na reinforcement na po pwede, but kailangan daw less doon sa minimum. Ngayon, meron tayong code provisions in terms of the minimum reinforcement ratio. Excuse me, I have to wait lang . I have to attend to this message. Okay, so balik tayo. Ngayon, yung design reinforcement dapat natin in order for the reinforcement to yield is mag-focus na yung actual reinforcement should be less than or equal to the maximum. Ngayon, before tayo mag-proceed doon sa maximum reinforcement ratio, siguro pwede nating tingnan kung ano ba dapat yung minimum. Okay. So, in code provisions, meron tayong minimum reinforcement na dapat sundin. Yung minimum reinforcement condition na dapat natin sundin ay manggagaling sa structural code wherein we derive it from section 409.6.1.2. Ngayon, under section 409.6.1.2, ang given daw dyan ay minimum area of steel. Yung minimum area of steel is whichever is greater. Whichever is greater doon sa 1.4 BD all over Fy and 0.25 square root of F prime C BD all over Fy. Ngayon, ito ay in terms of the area of steel reinforcement. Therefore, kung raw minimum ang hinahanap natin, paano natin i-convert itong AS minimum into raw? Paano natin gagawing raw yung AS? Alam natin ulit na yung principle ng raw is equal to the area of steel all over BD. So kung in terms of raw, ang gagawin lang natin ay it's either the greater of 1.4 all over Fy and 0.25 square root of F prime C all over Fy. Yan ngayon yung pagkukumparahan natin. So whichever is greater between 1.4 all over Fy and 0.25 square root of F prime C over Fy, yun ngayon yung mag-govern na raw minimum. Nagigets? Sabig sabihin,
Yes.
kung may nakuha ako na value na dito para sa 1.4 and para dito sa 0.25 square root of F prime C, eh nakita ko na mas mataas yung value nitong 0.25 kesa dito sa 1.4. Ano ngayon yung gagamitin kong raw minimum?
Yung 0.25 po.
Yung 0.25. Ngayon, itong raw minimum, madali lang naman siya gamitin. Paano ngayon natin kukuhanin yung maximum reinforcement ratio in terms of transition? Okay. Suppose, alam ulit natin na meron tayong principle na 0.85 F prime C AB is equal to AS Fy. Tapos, let's say this is equation 1. Assuming din na yung AS natin at this point is equal to the maximum at this point. Raw maximum multiplied by BD. Yan ngayon yung second assumption natin. At the same time, alam natin na yung value ng C na small is equal to, or sorry, hindi natin ano, yung value ng A rather is a fractional part of the value of C. which is equal to beta 1 C. Yan ngayon yung equation 3 natin. Para malaman natin yung maximum reinforcement ratio in transition, sinasabi ng structural code na ang maximum reinforcing or maximum net average strain na nakukuha ng steel is equal to 0.004. Diyan natin ngayon malalaman na yung reinforcement natin is in transition. Kapag yung epsilon ng steel or yung strain ng steel is equal to 0.004. Okay? So, paano ba natin gagawin ngayon yan? Given yung strain diagram ng both concrete and steel, kailangan nating makuha yung value ng C in terms of D. Ano yung pwede nating gawing relation dyan? Ano yung mapapansin yung relationship between this first triangle and this second triangle? Paano natin sila pwedeng i-relate? Okay. Kung meron tayong dalawang triangles with a similar side or similar ratio, ano yung pwede natin gawin? Pwede natin gamitin yung principle of may dalawang triangles tayo. Ratio and
Proportion po.
proportion. Pwede natin gawin na ratio or proportion or similar triangles, di ba? Ngayon, kung meron tayong dalawang opposite triangles, may simpler way para ma-solve natin yung ratio nila. Pwede nating i-extend yung other side para dalawang triangles ngayon yung kino-consider natin. Yung triangle 1 and triangle 3. Ngayon, given itong relationship na to, pwede nating sabihin na figure 1 and 3, pwede nating sabihin na 0.003 all over C is equal to ngayon. Pero tayong 0.004 plus 0.003 all over D. Ngayon, ang hinahanap natin dito ay yung value ng C. Wherein C is now equal to ano? Cross multiplication. Yung value ng C, or let's say, sige, yung value ng D. Kung yung value ng D ang hinahanap natin, sige, iano natin, cross multiply tayo para masaya. 0.003 D is equal to 0.007 C, which means the value of D is equal to 0.007 all over 0.003 C. Or pwede natin sabihin na this is equal to 7 over 3 C. Diba? This is equation 4. So, let's substitute. Let's substitute 2, 3, and 4 in equation 1. If we get to substitute equations 2, 3, and 4 at equation 1, we can actually get 0.85 F prime C multiplied by A, which is beta 1C, and yung ano natin na B is equal to AS. Yung AS natin is equal to rho max times B multiplied by D, which is equal to 7 over 3 C multiplied by Fy. Ngayon, dito sa mga terms na to, may pupwede tayong i-cancel. Ano-ano yung pupwede nating i-cancel?
B po.
Yung value ng B,
Saka po yung C.
yung value ng C. So matitira tayo doon sa mga coefficients lang na 0.85 beta 1 F prime C is equal to 7 over 3 rho maximum times Fy. Therefore, kung simplify natin yan, yung rho maximum now is equal to 3 over 7 multiplied by the quantity of 0.85 F prime C beta 1 all over F1. Yan ngayon yung maximum reinforcement ratio na kailangan natin gamitin if in transition. Paano ulit natin malalaman kung in transition yung design condition natin? In transition ulit if yung Fs natin is less than 1,000 but yung Fs natin is greater than Fy. Nakukuha?
Opo.
Okay. Ngayon, bukod dyan sa in transition, meron tayong another factor. Under maximum reinforcement ratio na tension control, same condition pa rin tayo ng tinitingnan. Tinitingnan natin na yung raw minimum must be less than the actual, but the actual reinforcement ratio must be less than or equal to the maximum. Ngayon, given itong instance ulit na to, kailangan nating ma-ensure na yung actual is less than or equal to the maximum. Pero, since tension control yan, dapat tinitingnan natin na yung yield strength, yung tensile strength ng steel or Fs should be greater than 1,000. Definitely, yung Fs natin dito is greater than Fy. Okay? So, alam daw natin na tension control, yung design condition natin if ang net tensile strain natin is equal to 0.005. So, tension control, if yung net tensile strain ng steel is equal to 0.005. Ngayon, given the same principles then as that of in transition, kailangan nating i-derive yung equation for the maximum design reinforcement. Ngayon, given itong maximum reinforcement ratio, pwede nating sabihin na ang condition ulit natin is compression is equal to tension or 0.85 F prime CAB is equal to AS Fy. But we all know na yung area of steel reinforcement natin is equal to rho maximum times BD. Baga, ginagamit lang natin parate yung principle na yung rho is equal to AS over BD. So regardless kung minimum or maximum siya or actual siya, same principle pa rin. Pero, yun nga lang, ang ginagawa natin kapag minimum and maximum ay nakadepende sa structural code. So yung actual, doon lang talaga natin makukuha sa AS over BD. So may mga sample problems din naman tayo na kailangan natin kuhanin yung actual reinforcement and yung mga actual na still area. Kaya itong topic natin na to na derivation ay masyado pang overwhelming for us. So, I know na medyo nakakasaturate itong maraming numbers or maraming factors na dapat nating i-derive. Pero kapag once meron na tayong actual na problem, feeling ko doon yung a-appreciate itong ginagawa natin. Kasi so far sa ngayon, puro pa tayo terms and nominal na variables. Okay. So AS again is equal to rho max multiplied by BD. Same time, yung ino-consider natin na value ng A is equal to beta 1 C. Ngayon, by principle of similar triangles ulit, taking figures 1 and 2, meron tayong certain change na mangyayari. Under figure 1 and figure 2, nakikita natin dito na may maiiba ng value. Which means that meron tayong 0.003 all over C is equal to 0.005. Okay. So ang iniba ngayon ng transition sa tension control is yung net tensile strain for transition is 0.004, whereas kapag tension control, ang reinforcement ratio na natin dapat ay 0.005. Okay, so 0.5 plus 0.003 all over D, which means that meron tayong 0.003 D is equal to 0.008. So 0.5 plus 0.003, 0.008 multiplied by C, which means that the value of D is equal to 0.008 all over 0.003 multiplied by C. Whereas this can be translated as 8 over 3 multiplied by C. So ulit, meron tayo equation 1, 2, 3, and another equation na 4. Ngayon, given itong equation na to, we can actually solve again the value for the maximum reinforcement ratio. So we must substitute, ibahin naman natin ng kulay para matandaan. So let's substitute equations 2, 3, and 4. Sorry, but may bilog yun. Yan. And 4 at equation 1. Isa-isay natin ulit. Meron tayong 0.85 F prime C multiplied by A, which is equal to beta 1 multiplied by C multiplied by the base is equal to AS, the rho max multiplied by the base, and then multiplied by the effective depth that is equal to 8 over 3 C multiplied by F1. Canceling the same terms earlier na kinancel natin, pwede nating sabihin na 0.85 F prime C beta 1 is equal to rho maximum times 8/3 of Fy. Therefore, pwede nating sabihin na yung rho maximum for reinforcement ratio na kino-consider natin in tension control or reinforcement condition rather, rho maximum is equal to 3/8 multiplied by the quantity of 0.85 F prime C beta 1 all over F1. Yan ngayon yung maximum reinforcement ratio natin if tension control. Tension control ulit, kino-consider natin na tension control ang design natin if ang tensile strength natin ng steel is greater than 1,000 and at the same time, the tensile strength of steel is greater than the yield strength of steel. So, kino-consider natin na nag-yield ang bakal natin if yung Fs is greater than Fy. So, makikita natin dito, kapag in transition sa tension control, laging Fs is greater than Fy. So malalaman natin yung value ng Fs base dito sa stress-strain diagram. Questions regarding maximum and minimum reinforcements? Or bakit importante na kinukuha natin yan? Importante na kinukuha natin yung maximum and minimum reinforcement kasi kailangan nating ma-ensure na ang design natin ay yielding. Ngayon, before tayo mag-proceed dito sa factored load combinations, meron tayong tatlong reinforcement conditions na dapat sundin. Sa tatlong reinforcement conditions, mag-iba tayo ng file. Yan. So, in terms of reinforcement condition, meron tayong sinusunod. Alam natin sa conventional na design, ang minimum dapat natin na reinforcement ratio should be less than the actual, but the actual should be less than or equal to the maximum. Ngayon, itong principle na yung actual is less than or equal to the maximum would denote that our design is under-reinforced. Or, pwede rin natin sabihin na yung tensile strength ng steel is greater than the yield strength of steel. Pwede rin natin at the same time sabihin na ang design natin is under-reinforced. Bakit? Kapag under-reinforced yung condition ng reinforcement natin, ang failure niyan is mas mauunang mag-fail yung steel. Before yung concrete. Ngayon, bakit importante na dapat maunang mag-fail yung steel bago yung concrete? Kung common sense ang pagaganahin natin, bakit importante na mauuna yung steel bago yung concrete?
Parang may warning po na may masisirang structure. Makikita po yung warning na may masisira yung structure.
Yun. So, nakikita natin na yung concrete, baga nagkakaroon pa lang siya ng minimum cracks before mag-fail. Tapos, alam natin na yung steel ay magbe-bend lang, hindi mapuputol, na magbibigay ng signal na either mag-retrofit na tayo or ibahin na natin yung structure. So, yan yung principle ng under-reinforced. Ngayon, suppose na yung actual reinforcement natin ay greater than the maximum. Anong condition ngayon yan? Ang condition na kung yung actual reinforcement natin ay greater doon sa maximum, ang nangyayari is over-reinforced tayo. Kapag over-reinforced yung structure natin, ang tendency is concrete will fail. Will fail before reinforcement. Meaning to say, yung concrete, babagsak na siya. Kumbaga wala nang wearing surface, yung structure natin, let's say, tinatapakan natin yung slab. Kung over-reinforced yan, bigla na lang siyang magka-crack, ugo na lang siya, pero yung steel is intact. Mas delikado para sa tao ang tumawid sa steel as compared sa tumawid sa concrete, di ba? At the same time, since ibig sabihin nun, yung concrete hindi enough yung compressive strength niya, therefore, kailangan natin ng another reinforcement para doon sa compression. Which means, kapag yung raw actual ay greater doon sa raw maximum, doubly yung condition ng reinforcement natin. Under this circumstance, na under-reinforced kanina, ang design natin dito ay singly. Meaning to say, kung singly reinforced yung beam natin, ang singly reinforced is nandoon lang sa tension part yung bakal. Pero kapag doubly, nasa both tension and compression yung bakal natin. Kumbaga yung holder bar na kino-consider natin doon sa itaas ay nagsaserve din as compressive reinforcement para makompensate yung compression na na-experience ng concrete na hindi na niya kaya. Okay? So, bukod dito sa under-reinforced and over-reinforced, meron tayong condition na tinatawag na balance. Okay. Under balance condition, wala na tayong tinitingnan sa reinforcement ratio kasi ang principle ng balance condition is concrete and steel will fail simultaneously. Yeah. So under balance condition, meron tayong kino-consider actually na raw balance. Pero itong raw balance na to ay galing sa 2001 na NSCP. So medyo obsolete na yung raw balance pero i-discuss natin next time for you to actually understand kung saan ba galing yung mga maximum na sinusunod natin ngayon as compared before. Kasi dati, under 2001 na structural code, ang raw maximum natin is equal to 75% ng raw balance. Pero ngayon, kung mapapansin nyo, yung raw maximum, pinahirapan nila ng onte. So, meron tayong kailangan kabisaduhin or i-derive para makuha yung raw maximum. Ngayon, under balance condition, walang warning yan. Kumbaga, kapag na-meet ni concrete sa ni steel yung strength na allotted for them, babagsak sila parehas at the same time. Okay? Question with regards to reinforcement conditions. Okay, recap. Dito sa tatlong design natin, dito sa tatlong reinforcement conditions, ano yung pinaka-ideal na gamitin?
Yung number 1, yung ano po, under-reinforced.
Okay, yung under-reinforced. Kasi ina-ensure ng structural code na kailangan daw yung ratio natin ng steel together with the strength limitations ay kailangan ma-meet. So, Yun yung isa sa pwedeng answer. And another possible answer for under-reinforced is because, yun nga, baga parang mas okay na magkaroon ng warning sign yung structure natin before mag-fail rather than nag-fail na agad na wala tayong magagawa. Okay, so balik tayo doon sa last topic natin for today. So, siguro hindi muna ako magsa-sample problem kasi alam ko sigurado na information overload na kayo ngayong araw dahil sa dinami-rami ng diniscuss natin. So, ito. So, our last topic for today probably is yung factored load combinations. So, out of the principle ulit na kino-consider natin na yung ultimate moment is equal to the strength reduction factor multiplied by the nominal moment. Ang tinitingnan natin ngayon dyan is yung applied. So yung applied na ultimate moment na to na MU can be related doon sa factored load combinations. Kasi mula dito sa factored load combinations lang tayo kukuha ng ultimate moment. Dahil, as we all know, itong VMN na to is considered as the allowable. Because yung nominal moment is in fact internal capacity ng concrete beam natin to withstand yung mga applied loads niya. Diba? Ngayon, out of these factored load combinations, whichever is the greatest among them, so meron tayong 7 na load combinations. Out of these 7 na greatest sa mga masasolve nyo in terms of application ng load or applied moment, yun ngayon yung gagamitin natin. Why? Because kung yung greatest load out of this 7 ang gagamitin natin, pwede niyang ma-resist yung natitirang 6. So, in these 7 cases, meron tayong dominant na loading. Usually, ang ginagamit sa practice is yung second term. Kumbaga kasi, given yung dead load, given yung live load, tapos kung meron kang gagawin na roof load or rain load, pwede mo na siyang isama. Pero, it is critical these days na dapat kino-consider mo yung effect ng wind and effect ng earthquake. Kasi, itong kino-consider natin na dalawa, let's say, 3 pala, rather, ito. Yan. Yung dead load and live load or yung roof load or rain load can be actually considered as majority na gravitational. Bakit? Kung mapapansin nyo, yung presence ng dead load and live load ay medyo dominant doon sa load natin. The same time, yung rain load na nandito is purely downward. Yung roof load natin lang yung dynamic dyan because sa roof load, kung may steel design na kayo, kay Engineer Sam yata kayo, di ba?
Opo.
Kay Engineer Olarte, i-discuss niya yung roof load na meron tayong 3 combinations na pwedeng gawin kapag may roof load. Baga meron tayong kino-consider na vacuum na compressive siya, or suction na hinihila niya yung bubong, the same time merong windward and merong leeward. So, yan lang yung medyo dynamic doon sa load natin. Pero yung dead load, live load, and rain load is purely gravity. Ngayon, dito sa 4 na to na natitira, yung kino-consider natin na 4, kung mapapansin nyo, yung wind load at earthquake load ay hindi siya purely gravitational. Bakit? Ang kinoconsider natin na nag-govern dito is lateral loading. So it is necessary na kung kayo as designers in the future, ang gagawin nyo dapat is i-consider nyo lahat. Lahat ng loadings na yan dapat i-consider. Kasi, baga, hindi mo po pwedeng sabihin na, let's say yung ginamit natin is yung 1.2 dead load plus 1.6 dead live load. Dagdagan ko na lang ng onting dead load yan, equivalent naman nung sa lateral. Hindi. Iba yung design approach ng lateral sa gravitational, of which madidiscuss natin later on sa lessons natin as we progress dito sa semester. Ngayon, paano ba natin makukuha yung ultimate moment of that? Sa RCD, limited tayo sa uniformly distributed load saka sa concentrated load. Hindi tayo magbabaringing load, okay? Magbabaringing load lang kung wind load or earthquake load ang gagamitin. Pero makikita nyo na itatranslate din natin siya into uniform and concentrated. So suppose na meron tayong beam, makukuha natin lahat yan doon sa maximum moment na makocompute natin. So kaya doon sa diagnostic test, ang pinakuha ko sa inyo ay maximum moment kasi from this given load combinations, doon tayo makakakuha ngayon ng ultimate moment na po pwedeng gamitin para ma-solve natin yung reinforcement and yung cross-section. Okay? Tanong. Or anything you need to clarify with regards to what we have discussed earlier?
Sir, yung U po ba na nire-represent sa may load combination, yun po yung tinatawag na ultimate moment?
Okay. Dito sa load combination na to, yung U na sinasabi ay ultimate load. Okay? Pero, syempre, kung in terms of moment na, yung dead load or yung live load or any other load, pwede mo siya ma-consider as ultimate moment na rin. Nagigets?
Opo.
Yun. Kasi may instances na given sa mga problems, okay, kung mag-a-answer tayo, kung magsasagot tayo ng mga problems, may instances na yung dead load or yung live load ay given na as moment. So, ibig sabihin, ang kukunin mo na lang is yung factored na ultimate moment na, di ba? Pero, kung halimbawa na beam, yung given na problem, tapos ang given ay dead load and live load, makukuha mo yung ultimate load. Di ba? Pero pagkakuha mo ng ultimate load, saka mo pa lang siya apply para maging ultimate moment. Nakakuha?
Yes po.
Okay. Questions pa? Anything you need to clarify pa? Wala na?
Wala na po, sir.
Okay. So, kung wala na kayong tanong, may i-discuss akong konti before tayo mag-dismiss. Ngayon, yung i-discuss ko with regards to the project na gagawin niyo ay i-flash ko in a while. So, ako yung mag-share na ng screen. Alam mo ka pala akong bagong design. Pasensya na, ang init-init kasi talaga. Wala rin akong aircon dito sa bahay. So therefore, kailangan ko magtiis sa electric fan. Okay, ito na yung laboratory activity natin. So narinig ko sa structural engineering majors na nakapag-group na yata kayo sa steel design under kay Ma'am Sam. Tama ba? Yung case din ba sa construction management na nakapag-group na under kay kay Engineer Sam?
Pinapag-groupings pa lang po ata kami pero wala pa po kaming na-form.
Okay. So, kung ano yung mapo-form nyo na grouping sa steel design, yun na lang din yung gamitin nating grouping sa concrete. Okay? Pero, napag-usapan namin ni Ma'am Sam na kung ano man yung gagawin ninyong building sa RCD, yun din yung gagamitin yung building for steel design. So ngayon,
Sir,
yes.
sir, bali po yung section B and A, pwede na pong mag-sum.
Yes,
Kasi-
pwede na mag-merge. Pwede na kayong magsama ng ibang sections. Okay lang.
Thank you po.
Yon. So, group yourselves into 5 and craft a 3-story mixed-use building with the following considerations. So, yung building natin kailangan 20 by 40 yung dimension. Tapos, ang condition is kailangan compliant sa building code in terms of habitable space and other standards which seems fit. Ngayon, you can use any sukat ng lupa, okay? Na magmamatch, syempre, doon sa building dimension nyo na magiging compliant siya sa building code. Oh my, ba't natanggal? Wait lang. Yeah. So, yung scale natin is 1:200 to 1:300. Pero provided na ang gagamitin ninyong papel ay A4. Ngayon, ang condition natin is walang typical floors. Ibig sabihin, hindi magkakatulad yung ground floor, saka second floor, saka third floor. Given din na yung function ng structure nyo ay mixed use. Ibig sabihin, kailangan halo na residential or commercial or residential saka commercial saka institutional. Kayo bahala kung anong function for as long as mixed use. Next, maximum center to center spacing ng columns ay 6 meters. Yung ceiling height ng ground floor ay 3.5 meters. Tapos, kailangan may backfill tayo na 0.5 meters. Meaning to say, yung column height mula NGL hanggang second floor should be 4 meters. Kasi, ang FFL ng ground floor ay 0.5 meters from NGL. Nakukuha. Tapos yung mga succeeding floors, yung second floor and third floor, kayo nang bahala kung ganong kataas yung height for as long as habitable space. Ayun. Yung structural members natin shall be limited of the following. Yung footing dimension, square footing tayo na 2 meters by 2 meters. Tapos may depth na 2 meters din at thickness na 650 millimeters. May beam dimension tayo. Okay. Sa beam dimension, this is according doon sa minimum natin sa structural code na at some point kailangan may width tayo na 300 meters and dimensions na 300 millimeters rather, 300 meters ulit. So 300 mm and then depth na 400 mm. Yung column natin is square column na may dimensions na 300 mm. Tanong. Sir, may kailangan pa po ba ng perspective? Hindi na natin kailangan ng perspective dito sa natin. Ang kailangan ko lang ay architectural plan saka structural plan. Okay? So may hindi rin pala ako nadagdag dito, slab. Thickness natin, iset natin ng 130 mm. Okay? Sa structural plan, foundation plan, saka floor framing. So dito sa case natin, dito sa 3-story mixed-use building, kung ano man yung gagamitin nyo sa steel, yun na rin yung gagamitin natin sa RC. Ngayon, kung sigurado ako na sa steel design nyo, nakatras yung bubong. Okay? Maki-verify kay Ma'am Sam na sigurado naman ako na nakatras yung bubong. So dito sa atin sa concrete design, okay lang din na nakatras na yung bubong. Hindi naman din natin siya kailangang isolve. Hindi natin kailangang isolve yung design ng trusses kasi sa steel nyo gagawin yan. Pero once nakuha nyo yung design ng trusses, merong weight dyan na corresponding. So yun yung gagamitin natin in order for us to design yung roof beam. So as we progress dito sa lesson, matuturo naman sa inyo kung paano gagawin yun. Pero for now, ang importante ay kailangan natin yung architectural plan saka structural plan. Sa architectural plan, ang kailangan ko ay floor plans saka elevation. Okay? Tanong. Meron pa pala dito roof framing. Kasi sa roof framing plan, nandyan din yung roof beam. Tanong. Nung una, originally, ang deadline natin ay April 2. Pero nakita ko na Webes Santo pala ang April 2. So, ang deadline natin ay April 8. Sir, paano po yung output nito? Or paano yung pagsasubmit? Yung pagsasubmit ay ganun pa rin. Kumbaga parang since 5 members kayo, dapat may 5 files kayo. Pero titingnan natin kasi medyo marami rin may unchecking nun. So feeling ko kahit through email na lang. Tapos yung group leader ang magsasubmit. Questions?
Sir, paano po yung sa roof framing? Kailangan na po ba dun yung sinasabi niyo po kaninang computation?
Hindi pa. Wala pa yun.
Okay po.
Ang kailangan lang is makapag-draft tayo ng plan na working plan nyo for this semester. Tanong pa? Wala na?
So far po sir, wala na. Pero baka po pag nagagawa meron na.
Yes, actually. Yun naman ang ano. Kumbaga parang as you progress, may maraming tanong yan. Okay? So, if wala na kayong questions or anything na kailangan i-clarify or wala nang violent reactions, so let's declare this class dismissed and ingat kayo. See you next week for our next lecture na sample problems for singly reinforced beams. So, thank you and ingat.
Thank you po.
Thank you po, sir.
Thank you po, sir.
Thank you.
Thank you po.
Thank you po, sir.